In the second lecture of the climb performance, we will study the second climb performance parameter, climb rate. At the beginning of this chapter, we already know there are two performance parameters in the climb performance. One is a climb angle, the other is a climb rate. Actually, the climb rate is measured by the vertical speed of an aircraft, usually is denoted as VC. And so in an aircraft as a pilot, you can see the vertical speed in the vertical speed indicator. And you can see this, the panel looks like the left-hand side picture, and it's measured by sensing the pressure difference when the altitude is changed. Now we need to know how to calculate the climb rate or the vertical speed. According to the definition of vertical speed, Vc equals dh over dt, which is a change rate of the altitude. And if we move our eyes to the right-hand side picture about the aircraft, Vc is actually a vertical component of the climb velocity v. So Vc equals v times sine theta. Now we need to know how can we express sine theta. And we've done this, the second law along the flight path, which is w over g times dv dt equals t minus d minus w times sine theta. So that's a force along the flight path. If we assume it's a steady climb, which means dv over dt is 0, and then we can have simplify the second law along the flight path. It becomes t minus d equals w times sine theta. And we can further write sine theta explicitly, t minus d divided by w. Okay, now what we can do is to plug in sine theta into the VC equation. It becomes v times t minus d divided by w. Okay, so physically we know Vt is a power available from the engines because force times velocity is power, has a magnitude of power. V times d then is the power required to overcome the drag of the aircraft. In the calculation or derivation of the climb angle, we define the excess thrust to weight ratio, T minus D over W, and similarly, in the calculation of climb rate, Vc, we define V times T minus D divided by W is excess power, which is in close similarity as the climb angle. Okay, the excess power can be transformed into an increase in kinetic energy, that's increasing airspeed, or potential energy, that's increasing altitude. Now we have the question, is there a best rate of climb? That means the largest VC, because we already know in a climb angle, there is a best climb angle, largest climb angle. Then we have the similar question here, is there a largest climb rate? We've just introduced the question, is there a best climb rate? We already know in the previous lecture, there is a best climb angle speed Vx. If the aircraft is flying Vx, it has the greatest altitude gain in shortest horizontal distance. And similarly, we have the best climb rate speed. We define it as Vy. So if the aircraft is flying at Vy, it has the greatest altitude gain in shortest time instead of shortest horizontal distance. We haven't yet answered if there is a largest climb rate velocity. So in order to answer that question and how to get it, we need to see through example, which is the same as we've seen in the first lecture. I'm not going to read through the question, but just to remind you, the thrust is assumed to be constant in this example or in this climb of the aircraft. And in order to find calculate the VC or maximum VC, we need to look at the equation of VC on the top right, and we know T is a constant and the W is also a constant, so it really relies on V times D. Okay, so since we can safely assume L equals W because it's small, the, the climb angle is always small. So then we can have CL equals 2W over rho V squared times S. And finally, CD can be rewritten as this. So we just, what we've done is just plug CL in the drag polar. Okay, finally, we can get the D, drag half rho V squared times S times CD. And we just plug in the CD in the equation. Okay, so finally we can have dv, and which is a function of the airspeed v. In the previous slide, we've derived v times d. That's power required to overcome the drag. So on the first graph showing here, we have T times V and D times V. So how the varies with the increase of airspeed. So in here, the airspeed increases in the horizontal axis from 50 meter per second to 250 meter per second. And we can see the red curve is D times V and the blue curve is T times V because we assume T is a constant, so it's a linear change. T times V is a linear change. Okay, so now we can focus to the red curve. And first of all, we can see the minimum value of D times V happens at airspeed of about 106 meter per second. And in this speed, in this airspeed, there is a minimum power requirement to overcome the minimum drag power. So at this speed, we define it as a minimum power speed VMP. So according to the curve here, it's 106 meter per second. So that's the physical meaning is if the aircraft climb at this VMP, it is climbing with the minimum power required. And since the VC is a difference between VT and VD, so we do the minus of these two quantities. So in the second graph, we are plotting TV minus dV, and again, it's changing with airspeed, true airspeed, and again, it's increasing in the horizontal axis from 50 meter per second to 250 meter per second. And we can see there is a maximum of TV minus dV. And we define this maximum climb rate speed Vy. It takes place at about 200 meter per second. So this is a maximum climb rate speed because when the aircraft is climbing at this airspeed, TV minus dV has a maximum, so VC is the maximum. Okay, so now according to these two curves, we can do the calculation based on the numbers provided in the question. So first of all, we know the aircraft is climbing at 315 knots, so we can find the climb rate, the current climb rate VC. So by plugging all these numbers, we have the climb rate is 15.68 meter per second. And now we can calculate the maximum climb rate speed. So Vy, we know Vy is 200 meter per second, and then we can have the Vy times d t minus d, so we get this number, and finally we can find the maximum climb rate or the maximum vertical speed. And this is just calculated based on the graphs, so it's a graphical method, and we can find Vc maximum is 159.3 meter per second. And similarly, and we can find a Vc when the aircraft is climbing at VMP. So we have VMP is 106 meter per second, and then we can find the difference VMPT times VMPD. So the vertical speed when the aircraft is climbing at VMP is about 84.9 meter per second. So it's apparently less than the VC maximum.